Logistic growth, a numerical approach. We already studied the logistic growth equation, and here's a way of numerically going through what's happening. It gives you added insight into what produces that equation. So that's why we're making this table. We're going to assume that we have k equals 10. We're going to work our way through here partially just so you get the idea. So we have 10 people that can potentially all get infected. They're all susceptible. Initially, we're going to have one with the flu. Everything starts with 1, I suppose. And you can list off 1 through 10. The number without the flu is just 10 minus 1, so 1 plus 9 is 10, 2 plus 8 is 10. 9 comes all the way down to 0. Number of possible interactions, well, 1 times 9 is 9, 2 times 8 is 16, 5 times 5 is 25. You just multiply I times k minus I. It spreads the most rapidly right here, and that's where it's 50-50. More than 2.5 times as fast as up here. As k grows, if k were 100, for instance, this multiple would be even greater. Now, we can calculate c is equal to RL divided by k. Why this is the case? Well, you really have to take differential equations to understand that. For now, just accept it as a given. Don't think too deeply about it. So 0.2 over 10 is 0.02. That's a proportionality constant. And that suffices to say that determines how rapidly this virus spread. If it was a very infectious disease like measles, for instance, C would be very high. If it was a very slow-moving virus like the common ordinary flu, would be a lot lower. So right now we're not going to connect that with anything. It's just 0.02. So here we multiply 0.02 times 9, which is 0.18. And now that's infections per day. If you take the reciprocal, it becomes days per infection. This tells us basically roughly 0.2 infections every day, which would take you 5 days for one new infection on the average. So we can do 1 over 0.18, and if you compute that, it's going to work out to be, that's my cell phone. I guess I could use that, but I'll use a calculator. Okay. 1 divided by 0.18 equals about 5.56 days per infection. We're going to assume our cumulative time up till this point is 0. 0 time has elapsed. And then we're going to proceed to the next row. 0.02 times 16, 0.32. And then we do 1 over 0.32 equals 3.125. We will take that 3.13. And then we'll add this to this and get 5.56. And then we just continue all the way down. Once we get to the bottom, we can predict the total time that it will take for full infection. And this will actually produce a logistic growth curve if you were to plot all this. So that's all for this simple video. We'll be back shortly with another one.